Welcome back to the deep dive. Today we are really strapping in for quite an intense look at something specific in aviation safety. It's what experts call one of the most, high-risk maneuvers, the near-ground go-around. You sometimes hear it called a rejected landing.
Yeah, and we often think about tailstrikes, right? That awful sound of the fuselage hitting the runway. We tend to associate it with maybe takeoff rotation being too aggressive or perhaps a landing flare gone wrong. But the safety sources we're digging into today, these are straight from Airbus. They're pointing somewhere else. A very specific moment, deciding to abort the landing and climb away when you're really close to the ground, often with minimal speed, low thrust.
That's absolutely the mission for this deep dive. We're taking the actual safety data, the specific case studies from the manufacturer. We want to understand not just what causes these incidents, but the precise, human and mechanical factors at play. We're basically trying to give you the operational shortcut to understanding why this maneuver demands such, flawless execution. And maybe we should start with a statistic, just to really set the stage for how critical this is.
Yeah.
Okay, so the sources, they tracked 49 tailstrike events reported to Airbus between January 2022 and September 2024. Now, landing itself accounted for 47% of those. But here's the bit that jumps out. 21 of those incidents, that's a stunning 43% of the total, happened during a go-around initiated near the ground.
Wow, 43%. That number is staggering, isn't it? It basically means almost half the remaining risk once you've flown a stable approach isn't actually in the landing touchdown itself, but it's concentrated in that split-second decision to bail out and climb away.
Exactly.
Yeah.
It makes this rejected landing phase a critical area to focus on, because the failure rate there is almost identical to the final touchdown phase itself.
Okay, right. So let's unpack the mechanism here. Intuitively, you decide to go around. The goal seems simple enough. Add power, pitch up, climb away. Why is this specific moment, the go around near the ground, so incredibly risky?
Well, it's a kind of physics trap, really. You're going from descending to climbing, right?
Yeah.
And that demands a high-pitch attitude to get the lift you need for a decent climb gradient. But, and this is the crucial part, if you demand excessive pitch when you're that close to the ground and your speed is low, the angle gets so steep that the tail, it hits the runway. And the single biggest human factor we see almost across the board in these cases, it's applying full back stick, just yanking it all the way back. That leads to this extremely high, often uncontrolled rate of rotation.
Okay, let's see how that plays out in a real case. You mentioned case study 1, an A320. This one happened during a bounce, you said. So the approach was stable, VAPT target 137 knots. But then, down at 80 feet radio altitude RA, so actual height above ground, the pilot flying puts in about a third nose down input. Maybe a small correction, but critically, at the same instant, the wind shifts. It goes from a 5-knot headwind to a 3-knot tailwind.
Yeah, and that's a classic recipe for losing lift suddenly. That combination, the slight nose down input plus the loss of headwind, it just caused lift to decay rapidly. So the vertical speed shot up, or down rather, hitting minus 800 feet per minute by 40 feet array. And even though the pilot initiated the flare, they still touched down the first time with an already high pitch plus 9 degrees, which led to a light bounce.
Okay, and here's where it gets really interesting, you said. This is the critical part. When the pilot decides, okay, go around, selects TOGA thrust, they apply full nose-up input. But the sources pointed to something else as well, a subtler error just before that.
That's right. The subtler error was the continuous, non-stop application of nose-up input during the whole bounce. It lasted about 2 seconds. The pilot was, fighting to stop the plane touching down a second time. Understandable, maybe, but wrong. So that continuous input, combined with the final full-back stick demand when TOGA was selected, that's what caused the pitch to rocket up from that initial 9 degrees to a critical plus 12.7 degrees at the second touchdown.
And the speed must have been bleeding off significantly there, too.
Oh, absolutely. The tailstrike itself happened at 127 knots. That's 10 knots below their target approach speed, BAPP. But the really critical insight here, and it feels counterintuitive, is that the pilot's attempt to prevent that second touchdown, by holding that continuous nose-up pitch during the bounce, that's precisely what put the aircraft in the perfect attitude for the strike. The procedure is actually to allow the aircraft to settle, potentially touch down again lightly, before adjusting pitch further and retracting controls.
Wow. So it's that human reaction in the moment, maybe a bit of panic, the overcorrection on pitch, that proves catastrophic.
It often is. Now, let's maybe shift to case study 2. This involved an A330. And it highlights slightly different issues, less about a bounce, more about energy mismanagement and crew coordination. Okay, so the initial problem here started earlier. The source mentions chaotic control inputs. The pilot was sort of alternating between nose-up and nose-down inputs between about 90 feet and 30 feet. This increased the vertical speed again, up to minus 850 feet per minute this time, which led to a late flare and then a hard touchdown.
But the tailstrike wasn't on that initial hard touchdown?
No, it happened just after. The pilot flying, the PF, kept some nose-up input after the touchdown. Then, realizing things weren't right, applied full nose-up and J thrust. But crucially, this decision was made when the aircraft's speed was dangerously low. It bottomed out at only 116 knots. That's a whole 23 knots below VAPP. Just not enough energy. The pitch hit 10.9 degrees, and that combination minimum energy, aggressive rotation, caused the tail strike.
Okay, this brings up the other pilot, right? The pilot monitoring, the PM. The source mentions the captain tried to intervene. A brief 1/3 nose-down input. And that triggered a dual input call-out, which really highlights the danger around communication or lack of it in a crisis.
Yes, and this is a really vital safety point, especially in aircraft with sidesticks. The danger comes from how the system works. The sidestick inputs are algebraically added together if the priority takeover button isn't pressed and held. Now, in that specific A330 case, the captain's small nose-down input wasn't actually enough to counteract the PF's full nose-up command to prevent the strike. But the broader risk, the one the source material really emphasizes, is if both pilots accidentally push the stick in the same direction. Imagine, say, both apply 2/3 nose-up simultaneously without coordinating. The flight control computer just sees the sum of those inputs. It interprets that as a single command for rotation, which could potentially exceed the normal full control limits, or at the very least ramp up the rotation rate much faster than is safe near the ground.
So the risk isn't just confusion about who's flying. It's that two partial, uncoordinated inputs can add up to one massive, maybe even maxed out command, rapidly accelerating the pitch, demanding a rotation the aircraft just can't handle safely at that low speed.
Precisely. The system gets one combined instruction, and this is exactly why the standard operating procedure, the SOP, is so strict it's non-negotiable.
Yeah.
Only one crew member flies the plane at a time. You need a clear transfer of control, I have control, and the use of that priority push button to electrically lock out the other stick.
Okay, so given these, disastrous input scenarios, what are the clear operational fixes? What are the sources telling crews to do? It sounds like the fundamental takeaway is managing pitch and energy very carefully, precisely, and definitely not aggressively during this maneuver.
That's the core message, yes. The source material really boils down the prevention strategy into 3 critical operational rules for a safe near-ground go-around. First, pitch monitoring. This isn't just on the PF, it's a shared job. Both pilots, PF and PM, must carefully watch the pitch attitude. The PM has to make that standard PITCH call-out if it reaches the limit set in the SOP. Second, avoid excessive rotation. We've seen it in both cases, haven't we? Full backstick is a primary cause. Crews have got to be disciplined. Avoid that instant full nose-up demand. And third, delay retraction, meaning hold off on retracting flaps and landing gear. Wait until the aircraft is definitely established on its go-around path, climbing away safely.
Why is that so important, delaying retraction?
Because retracting flaps too early reduces lift. That forces the crew to compensate with an even higher pitch attitude, precisely when they're closest to the ground and most vulnerable to a tail strike.
Right. Let's zoom in on that energy state you mentioned. It seems critical. If the engines are at idle when the go-around starts, which seems likely during the flare, right? There's that spool-up delay before you actually get TOGA thrust. What's the rule for rotating the aircraft during that lag?
The rule is very clear, and it has to be followed. The crew must wait until the aircraft's speed gets back up to at least VAPP. Only then should they demand significant pitch-up or rotate the aircraft strongly. This mandatory wait, it might only be a few seconds, but it's absolutely essential. It gives the engines time to spool up, generate thrust, and it lets the airframe gather enough speed and lift to handle the increased pitch safely without dragging the tail. Demanding rotation 23 knots below VAPP, like in case 2, that's just asking for trouble.
Okay, and circling back to that first case, the bounce scenario, how should crews handle actually making contact with the ground if they start the go-around really late?
This is a huge point for training, for managing that human reaction. Brief landing gear contact. It might happen if the go-around is initiated very, very close to the runway, and it's considered acceptable. The pilot absolutely must not try to avoid that contact by yanking the stick back even harder, increasing pitch further. That reactive impulse, pull back harder to avoid hitting the ground again, that's the error that leads directly to the tail strike. So if the go-around starts during a bounce, the procedure is maintain the current pitch. Allow that potential second touchdown to happen, let the aircraft settle, let it gather speed, then adjust pitch for the climb and retract controls. Don't fight the second touchdown aggressively.
Okay, that makes sense. Now, we need to talk about the absolute point of no return. The crew has maybe seconds to make this call. When is it definitively too late? When do you have to stick with the landing?
The SOP is mandatory on this. Absolutely clear. The flight crew must not initiate a go-around once the thrust reversers have been selected. Selecting reverse thrust is a hard line. Once you do that, you are committed. You have to stop the aircraft on the runway you have left.
And just connecting the dots, why is trying a go-around after selecting reverse thrust so incredibly dangerous?
It creates a catastrophic energy deficit. It's physics again. Selecting reversers kills your speed rapidly. Plus, those reverser doors have to retract and lock before the engines can even start spooling up to full forward thrust. So you're burning precious time and runaway distance with your speed decaying fast. By the time you might actually get TOGA thrust, your speed could be disastrously low, even worse than that A330 case we discussed. It's just an unacceptable risk profile.
Okay. So finally, how do we fix this? How do we train for it better? The source seemed to have a clear idea for simulator training to address these repeated errors.
Yes. The training recommendation is really targeted. It's based on recreating those specific low-energy, high-surprise conditions we see in the real incidents. Instructors should basically trigger the go-around instruction at the exact moment the thrust levers are already being retarded to idle for the flare. This simulates that highest risk condition: low speed, minimum thrust, minimum altitude. It forces pilots to practice those precise, non-aggressive pitch inputs and that critical energy management waiting for VAPP if needed. That's what makes the difference between a safe, rejected landing and a costly, dangerous tailstrike.
Right. That really brings us to a solid summary then. A safe go-around near the ground needs precise, gentle pitch inputs, no yanking, careful energy management, especially waiting for VAPP if you start it from idle thrust, and really strict adherence to crew coordination rules. No dual inputs, clear communication.
And maybe my final thought for you, for the listener, is this. This data, it isn't just about aircraft mechanics. It's fundamentally about human psychology under pressure. Think about it. That dynamic phase of landing, you're shifting mindset from stop the plane to full power climb in milliseconds. Often, your focus is entirely out the window. Speed is dropping. Thrust is already low. The data really shows the danger lies in that human tendency, maybe panic, maybe just instinct, to overcorrect, to go for that immediate full backstick demand during that chaotic transition.
That's a really powerful point, connecting it back to the human element, the decision-making under extreme stress. It's not always the machine, sometimes it's the reaction. Definitely something to mull over next time you think about those final moments of a flight. Thanks for joining us for this deep dive into the source material.